Where did we get to? All right, so we're talking about sterile filtration. So let's finish talking about sterile filtration. And if you remember, just before we took our break, we were talking about the fact we need interconnected pores and so forth. So typically, this is what is done in industry. We talk about a Vmax and a Pmax analysis. So maximum volume that you can process and maximum pressure. And it's the simplest approach to sizing normal flow filters. So these basically these sterilizing grade filters. So flow decay method, in which the cumulative filtrate volume is measured through a small area test filter until the flow rate drops to 10 or 20% of its initial value, right? So you have a constant pressure, you keep running it, and eventually it drops, and then it gets to 10%, and you stop there. Data are then extrapolated to larger production volumes, assuming the filter performance scales linearly with membrane area. Okay, so you do this on a small scale, and then you scale up, and you say, if I just increase the membrane surface area, I can linearly increase the volume I process, and you come up with an answer. The disadvantage is that large volumes of process fluid required to achieve 80 or 90% reduction in flux, so similarly limiting the amount of testing that can be conducted in a cost-effective manner, particularly during early stage of product development where feed is limited. So remember, in the biotech industry, these feedstocks are rather expensive and difficult to get. I mean, you can't produce very much very quickly. And so you're scaling, assuming that this is linear, right? But it's very difficult. So typically, we scale up maybe 5 times, 6 times, something like this. But here, you're trying to extrapolate. And if it doesn't work, you have a serious problem. So that's the limitation. But that's typically how that is done. The Vmax analysis is a different one. So the flux decay data obtained over only a short filtration time, typically 10 to 15 minutes, are then extrapolated to longer filtration times using the linearized form of the flow constriction model as shown here. So you get your data, right, for a short time, and then you plot it using this model here. But this is actually one of the equations I showed you earlier for pore constriction. So you plot it this way, and then you extrapolate, okay, for longer times, right? So inverse of the slope of a plot of T versus V, T divided by V versus T maximum. T is the maximum volume of fluid that can be filtered before the membrane is completely plugged. Scale up accomplished by assuming available capacity, usually 50 to 80% of the maximum. Scales linearly with membrane area. Vmax requires smaller volumes of process fluid and shorter testing times, but may lead to large errors in the predicted capacity if fouling does not occur due to pore constriction, okay? And so this is where I say that when people use these models, often they don't think about what the assumptions were. So this is very common. If Millipore or someone else is trying to sell you a filter, they use this actually as a scale-up method. And then they will do it to scale up something, but actually the sales rep, whoever, really doesn't understand how this comes about, right? It just uses a Vmax model. That's common in industry. But it assumes pore constriction. So in fact, if the feed stream you're looking at is not fouling because of pore constriction, you may get very wrong results, you see. So this is one of the things to be very careful of when you're trying to scale up, and especially if you're working for a biopharmaceutical company, it's quite important because people just use these models without thinking of the assumptions that went into them, okay? So here's an example. Look at this. So here we say, what are the limitations I say here? So PVDF has a much higher capacity due to lateral porosity. So let's read this. This is Vmax analysis for BSA filtration using 0.2 micron polycarbonate track etched membrane. That's what PCTE is, okay? These are the circles you can see here. And a 0.2 PVDF membrane, and the PVDF is given here with the squares. Solid lines are model calculation. Dash linear regression fits using data obtained for T less than 10 minutes. So for T less than 10 minutes here, you regress this. PVDF has a much higher capacity due to lateral porosity, so it's got a lower slope, okay? This is PVDF. For PVDF data, under determines capacity, which could lead to significant scale-up errors, because you see, this may look like a small error here, but if you scale up, it could be a very big error, okay? And again, these errors are coming because you are using data for a very small amount of time and extrapolating to very long times. But you have to do that because you don't have enough fluid, enough feed stream to do much longer times, you see. And so all I'm saying is here that scale-up of these devices is often quite tricky. And many times people try to design purification trains and then they don't work. or there are problems, and especially with sterile filtration, which is a fairly simple process actually. A similar approach can be used for constant filtrate flux. That was all constant pressure. Total resistance is equal to the ratio of transmembrane pressure to flux, plotted as a function of volume filtered per unit area. So if you think of it, we said the flux is equal to what? The driving force divided by the resistance. So what we're saying here is total resistance is equal to the transmembrane pressure, the driving force divided by the flux, right? That makes sense, right? Okay. If fouling is due entirely to pore constriction, pressure P will increase with cumulative filtrate volume given by the following expression. It's in the earlier slides that I showed. P naught is the initial pressure, V max is the filtrate volume corresponding to complete saturation of all pores. Similar equation derived based on pore blockage model, but with the exponent of -1 instead of -2. Capacity defined based on predetermined pressure and endpoint. So why is capacity based on a predetermined pressure and endpoint? So the reason is you run these. So depending on the, if it's a constant flux, you go to a certain pressure. But at some point, the pressure is too high, right? It's not practical to go to higher pressures. And this could be many reasons. It could be a pump restriction. It could be many other reasons. So that is your predetermined endpoint, right? So in your scale up and so forth, you say this is the endpoint. That's why that is the case. Alternatively, endpoint may be defined based on measurements of filtrate turbidity if no significant breakthrough of debris at high loading occurs. So I also told you turbidity is important. So you can look at turbidity. If it's going up, that's your endpoint. But whatever it is, you always set an endpoint, and then based on that, you're doing your scale up. The Pmax method provides much more reliable scaling than Vmax. Use of constant filtrate flux highly attractive for direct flow normal flow operations. So we talked about this earlier, that certainly for bioreactor harvesting, we always use constant filtrate flux as opposed to pressure, and it's attractive because you prevent fouling at those initial stages if you had very high filtrate flows, and that is particularly true for microfiltration processes. Okay. Okay, so sterile filters are 0.1 or 0.2 micron pore size. So I did want to point out something because we've talked a lot about pore size, right? 0.1, 0.2, 0.45, and so forth. But you realize these are all nominal pore sizes, right? I mean, how do you say a pore is exactly 0.1 micron? Because these are all membranes with a variation of pore sizes. There's not just one pore size. It's not a track-etched membrane. So when we say 0.1, what do we mean? When we say 0.2, what do we mean? When we say 0.45, what do we mean? Sorry? No, not really. So for 0.1 and 0.2, if they're sterilizing grade filters, it means that there are various specifications here for removal of certain microorganisms under standard conditions. And so you have a fixed pressure and fixed operating condition, fixed concentration of your microorganism, you're saying you're rejecting it. Okay? So the smallest pores may be much smaller. Okay? They may be much, much smaller. And so that's why when you get 0.1 micron pore size membranes from different manufacturers, they may actually give different performance under actual operating conditions, okay? For exactly the reason you said, because we don't know what the smallest pore size or the largest pore size is. We just know under these standard conditions, the manufacturer claims it rejects whatever the model bacteria is, and this is all standardized. And at a certain value, right? So it rejects these. But under your actual operating conditions, that may not be the case. This is particularly true, say, in ultrafiltration, where you talk about nominal molecular weight cutoffs, and you talk about, 90% BSA rejection. And two membranes that are nominally, say, 100 kilodalton may perform very differently under actual operating conditions, okay? So one has to be careful. When you say 0.1, 0.2, these are not absolute values. This just gives you an idea of what it is. In reality, you have to test it for your feed stream. 0.2 micron filters here are based on the removal of 10 to the 7 colony forming units. Actually, I need to get my pointer back. 1 second. Okay, so 0.2 micron filters are based on removal of 10 to the 7 colony forming units of this particular virus per centimeter, bacteria per centimeter squared membrane area. So that is the definition, okay? So if a membrane meets that, it's 0.2 micron, okay, basically. It could also be 0.1 micron, but it meets the 0.2 micron definition, okay? So it's used throughout the purification process for recombinant DNA-derived proteins. Cell culture operations may use 0.1 and the mu is missing, 0.1 micron membrane to provide protection against microplasma in raw materials. So you may use a tighter pore size, but typically 0.2 is used. Membranes for this sort of operation for sterile filtration are made from polyether sulfone, PVDF, nylon, or polypropylene. Many base membranes have a surface coating or are cast as polymeric alloys to reduce protein adsorption and fouling. So I told you that for the sterile filtration operations, actually capacity is very important, right? You want to maximize what you can run through this. And they are also going to be removing aggregates. But you don't want them to remove your product. You don't want your product adsorbing on them. And all the materials, well, most of them I mentioned here, PVDF and polypropylene are hydrophobic. And so you surface coat them to try and suppress basically adsorption of proteins, okay, or of species, non-specific adsorption. Chemical modifications focus on rendering the membrane more hydrophilic, lowering zeta potential to avoid ionic interactions. Okay. So microorganisms are removed by size exclusion. That's why we define a nominal pore size, and we have a standardized way of saying what's happening, 10 to the 7 colony forming units, so forth. Removal of protein aggregates occurs by size exclusion, but much more by adsorption onto the surface, right? Because the protein aggregates are going to be much smaller, typically. If you've got very large aggregates, you know, the size of a microorganism, you've got a problem with the process, okay? And that's not good. If you've got, you know, micron-sized aggregates, you're losing a lot of protein. Something is wrong. Protein aggregates form over time during product hold steps between unit operations. So you remember that diagram I showed you, the various unit operations? So remember, these are fragile proteins, and they're going through this process, and typically it takes more than 1 day, because sometimes one of these operations takes 1 shift. So it may be a chromatography column 1 shift, a polishing step the next shift. So it may take a couple of days, may take a week for it to go through this whole process, okay? Sometimes they run at 4 degrees Celsius, sometimes they run at room temperature, that depends, okay? So as it goes through, you will get deformation of some of the protein and loss of some of the protein. So these aggregates do form during the whole process, okay? And that's why there are so many repeated sterile filtrations to try and remove aggregates. Higher level of aggregates occur in steps such as ultrafiltration, when protein is subjected to multiple passes through pumps and valves. That's why we're showing you that alternating tangential flow tries to prevent running through the pump a number of times, because running through pumps creates shear stresses that actually damage the protein. Okay? Significant turbidity may be observed after some downstream processing operations due to strong dependence of light scattering on particle radius. Static light scattering intensity, so this is important. Intensity measured as a function of scattering angle is proportional to r cubed, while dynamic light scattering signal from temporal variation of intensity is proportional to r to the 6th, where r is the particle radius. So all I'm trying to say here is that because it depends on r cubed and r to the 6th, actually turbidity measurements, sure, they tell you you've got aggregates, but it may lead to the idea that there are many more aggregates than you think, because it depends so strongly on radius, okay? So an increase in turbidity doesn't necessarily mean you're losing huge amounts of protein, but it does mean you have aggregates there that you need to remove, okay? So turbidity measurements are actually used, they're a quick test, they're used quite a lot. Yield loss due to generation of insoluble aggregates usually less than the limit of quantification. So usually it should be low in a well-operating process, okay? The generation of salt, now I should talk about this. So, you know, we talk about contaminants being product derived. So there are aggregates. These are actual aggregates that form. But there are other things. There are things called soluble product multimers and dimers. So if you like, 2 or 3 product molecules can associate with each other. They don't necessarily form an aggregate, but they are associating with each other. And this can cause problems because it can plug the pores of a virus filter and so forth, okay? But they may not actually be insoluble aggregates. You also get denatured and deformed products, product variants, and different glycosylation and so forth. All of these can actually cause problems. But as I said here, generation of soluble multimers downstream processing is rare. Aggregation typically due to microcavitation in pumps and valves. Microcavitation leads to protein interfaces that in turn lead to protein denaturation and aggregation. I did mention earlier that liquid air interfaces are very bad, okay, because they will cause protein denaturation. Protein aggregate adsorption and retention becomes capacity limiting for feed streams with low microbial levels. That makes sense, right? So sterile filtration, if there are not much microorganisms there shouldn't be, then what's going to limit capacity is going to be the presence of protein aggregates. Removal of aggregates is important part of the purification process, important for filtration of a final bulk product. Further aggregation after the last step in the process avoided by proper development of instrumentation for formulation buffers and excipients. You know, as you go through the purification step, you're ending up with more and more highly purified protein. And at the very end, you have a final fill step where you take this and you put it in some sort of buffer, and then it's shipped off somewhere else, and it's made into whatever form it's going to be, is a tablet or injection, whatever, okay? It needs to be stable in that. And so the final buffer is often quite different to the various processing buffers along the way. It needs to be stable, and one puts excipients, which are other sorts of species that basically stabilize the protein. Okay, so you put additions there that lead to stabilization of the protein. Okay, so there are many different polymers. Manufacturers also have the ability to cast a number of different membrane structures. So when we think of, and this gets back to chemistry, when you think of trying to optimize membranes for biotech applications, there are many different polymers. We'd like to work with polymers that are regulated, that are actually have approval from regulatory authorities. So things like PVDF, polyether sulfone, regenerated cellulose, these are ones that are routinely used. So you'd like to work with those. But there are different ways to cast these. You can do surface modification. So there are various things that can be done to enhance the properties of the polymer. Various production methods are used depending on the polymer and the desired structure. Methods include air casting, immersion casting, melt casting, track etching, stretching, and radiation-induced polymerization. So some of you are aware of some of these techniques, right? Casting may also be performed using another membrane as a substrate, often referred to as a composite membrane. So earlier I talked about symmetric and asymmetric, right? So if you think of it, symmetric membranes are made from one polymer. You don't have multiple polymers. One polymer and everything is uniform. Asymmetric membranes could be made from one polymer where you have a gradation in pore size. So there's a very thick or very thin barrier layer that typically faces the feed in ultrafiltration, and then a more open structure, but it's still one membrane. But you can also have composite membranes, which gives you more degrees of freedom, where you take a support structure and you cast a membrane on it. And all of you know about reverse osmosis membranes, which are thin film composite membranes. But composite membranes are also used for virus filtration, sometimes for ultrafiltration. Microfiltration is rare, okay? Anyone can think of why it's rare for microfiltration? Well, what's the purpose of having a composite membrane or an asymmetric membrane? I mentioned it earlier. Anybody remember? It's because if you have a very tight barrier layer and the whole membrane is that barrier layer, you have very high resistance to flow, right? But if you have only a thin barrier layer, you have no mechanical strength. Right, so with microfiltration membranes, actually they're very open, right? So the barrier layer is really very open, so you really don't need a thin layer. The support structure is usually sufficient. So it's rare to have composite microfiltration membranes, okay? Okay, what else? Okay, structural characteristics of a membrane play a major role in determining the permeability, retention, capacity, process flux, and process capacity. Developments in production of composite and multilayer membranes have provided dramatic increase in membrane capacity compared to isotropic membranes used for sterile filtration in early bioprocesses. Okay, so today, typically these sterile filtration membranes are not isotropic. Okay, and the very important word here is capacity, which is we want to maximize the number of liters we can process per membrane surface area. Okay, so a little bit more on isotropic and anisotropic membranes. Isotropic membranes have a uniform structure throughout the depth of the membrane. Permeability is dependent by pore size distribution and thickness of the membrane. When filtering particles larger than the pore size, process capacity may be limited since retention is at the surface of the membrane. Okay? Anisotropic membranes have a graded pore size distribution that varies throughout the depth of the membrane. Permeability enhanced with these structures while still maintaining the mechanical strength of the membrane. We talked about that, right? You have a barrier layer, so they're asymmetric. Process capacity is enhanced for feed streams that have a wide particle size distribution as different sizes retained by different layers, and that's this reverse asymmetric idea. Anisotropic membranes may also be used with the smaller pore size on the upstream side, advantage for feed streams, relatively homogeneous particle size distribution, and small loads where surface is adequate. So, we talk about this reverse asymmetry, and that's particularly useful when you have a range of particle sizes, right? Because you can trap larger particles at the start and smaller particles later, and so it provides higher capacity. It's also very useful when you have a high load of particles, because you get this idea of a stabilized membrane. If you're looking at surface filtration, your capacity is much less, right? Because everything's blocking on the surface. However, you can run at higher fluxes, because I told you for the reverse asymmetry, you don't want stuff to go and start plugging your pores. So the advantage of having the other way is you can run at higher fluxes if you're talking about dead-end operations. And so when you have a low load of rejected species, in other words, when you're doing a sterile filtration of a buffer, for example, right, because all buffers are sterile filtered, there should not be anything there, right? There shouldn't be microorganisms there, and there shouldn't be any aggregates. If it's an aggregate, there's a big problem. This is not a well-prepared buffer. In that case, if you use it with the barrier layer facing the feed stream, you should be able to get much higher fluxes, and it runs very quickly. So that's what's meant by that, okay? All right, so I wanted to show you some photos of this. This is an evolution of casting technology for sterile filters showing progression from A. So this is isotropic. Isotropic schematically is this, right, where you have a straight through pore. And then this is anisotropic, where if the barrier layer is facing the feed stream, the pore size increases as you go through, where the bottom part here is the support structure, okay? And then you have this idea of a composite membrane, or co-cast membrane, where you can see you can have a very, very small pore size on a larger one, and then it's on another one, and you have these various different layers, right? And the reason that that's useful is that you can then use polymers with different properties, and you cast one on top of the other, so you can actually have more flexibility in the polymer, okay, and the whole structure. So composite membranes combine two different structures into a single membrane. Different layers independently formed with either isotropic or anisotropic morphology, having distinct pore size distribution, aspect ratio, that's the ratio of pore size to the two faces of the membrane, and thickness. It provides many degrees of freedom to tailor structure to various types of feed streams. One of the layers may be, in fact, a pre-filter to the previous one, so I was showing you here. See, this could be actually designed such that the layer on top is a pre-filter to the one before, and so forth, especially if you use it in the reverse asymmetric geometry. And so today, actually, a number of membranes, Millipore makes a number of composite membranes, and they have much higher capacity. We are always trying to increase capacity, okay? The multilayer membranes physically layer two different membranes together, each cast separately with desired properties and pore size. The first layer is typically used as a pre-filter, with the second layer an absolute value rate as 0.1 or 0.2 micron, okay? I had a little bit of other information here about actual membranes. So most common sterile filtration cartridge is called code 7 design, which refers to the bottom adapter. So this is just the way it's designed, okay? And the way it's in a steel housing. And they come in 10, 20, 30, and 40-inch high configurations. Other cartridges also exist. The main point here is that there are fairly standard ratings for these sterile filtration systems, okay? Pleating technology is used to improve scale-up and process economics obtained by using novel membrane structures and by increasing packing density of the membrane inside the cartridge. Pleated membrane packing density is approximately twice as high as traditional cartridges by using longer pleats and rotating in a tight pack. Increased membrane area has the benefits of higher capacity and smaller housings, okay? I think the next one gives you a photo, yes. So you can see here a comparison of the density of these pore membranes, okay? So you can see here this is a star pleat and a different sort. So you can see doing these different structures, you're actually forcing more membrane surface area in there. So the pleated idea is interesting because you can, it's like if you think of water treatment, you have spiral wound membranes, right? And you have flat sheets and you have hollow fibers. So spiral wound is very nice, right, for reverse osmosis because you can have a lot of membrane surface area in a very small volume. But it's not very good if you have lots of particulate matter because you can easily block your channels and they're impossible to clean. Similarly here, if you are trying to filter buffers, there shouldn't be any particulate matter. And so the more membrane area you can compress, the better it is, right? Because you get smaller units, you have less losses, and you can have higher capacities. Okay, so that's basically what this is about. Kind of come up with novel structures for these membranes. Processes. So we can have so-called flux limited and capacity limited operations. So flux limited means that we can only go to a maximum flux and we cannot be there. Capacity is very important because we can only treat a certain amount of material per surface area, and then after that the membrane fouls, you have to throw it away. So there are two different types of operation. Flux limited applications include purified water and simple solutions such as buffers and media. As I mentioned earlier, if you're putting water into the system, you're putting buffers into the system, they all have to go through a sterile filter. However, they should not be capacity limited. There should not be anything there, right? So nominally speaking, you can run forever, right? This should be a fresh buffer you prepared under sterile conditions anyway, and so it's just an additional protection. So therefore, the limitation is flux. You run it as fast as you can based on your maximum pressure, right? So it's flux limited. Most feed streams are capacity limited with the maximum capacity depending on operating conditions, right? So if you have a CHO cell stream, some particles in there, then it's going to be capacity limited because you're actually removing stuff, okay? And it's going to depend very much on the operating conditions. Study needs to be performed to establish optimum flux that results in the filter size that can both process a given volume in a given amount of time while providing adequate capacity. This is what I mentioned earlier. So people run under constant flux mode for microfiltration. If not, you will have very high fluxes at the start, which will tend to reduce your capacity because you will get a lot of fouling at the start. So these are optimization studies. And actually, typically in a manufacturing process, you have various tolerances, right? You can operate within certain pressure ranges and so forth. And so this is all highly automated and controlled. Capacity studies performed using either constant pressure or constant flux. Appropriate study will depend on the intended mode of filtration. Constant flux will result in higher throughput capacities generally for things like microfiltration. Okay. So I think this brings me just about to the end of the sterile filtration applications. I just wanted to show you where we are in all this. So we talked about bioreactor harvesting. We talked about sterile filtration. We have a few other things to talk about in terms of tangential flow microfiltration. And then we're going to talk about virus filtration and then membrane adsorbers. So that's basically where we are at the moment. Let's go back to this figure because I always like to make sure that you remember where we are. So what we've talked about then is all sorts of sterile filtration operations all over the place here because we are introducing media, right? So there's these sterile filters that we've talked about. We've talked about a replacement to all this using depth filters, right? I should point out that this course is about membrane-based bioseparations. So don't think that only membranes are used in this process, right? These other applications are very important, okay? And so we talked about the possibility of replacing all this and using depth filters. And then we have more sterile filtration operations here that occur during the whole process. And then I think that's almost the last slide. Yes. So if we look, this just highlights the downstream purification part. So I just want to highlight again. See, you have a sterile filter here, 0.2 micron. You have a sterile filter here. You have a sterile filter here. You have a guard column here, right, for your chromatography steps. That's typically a depth filter. So you can see what a lot of membranes we use in all this. You have another sterile filter here at the very, very end, right? And you may have other sterile, you will have other sterile filters when you have buffers entering this system. So we have talked about a number of these different membranes that are used in the whole process here, okay? And then I always wanted to end with talking about future directions. So the future directions are firstly continuous biomanufacturing. So how would you do a sterile filtration operation for continuous biomanufacturing? That's a challenge, right? Because you want to run this now for, let's just say 1 month, all right? So how are you going to run this? Because it means you cannot change your filter for 1 month. It has to perform. But there's another difference too. I was talking earlier about flux limited, right? So you want to run as high a flux as possible, But actually, for continuous biomanufacturing, it's not, flux is not important. You're going to run for a month anyway. So you're not concerned about trying to get everything done quickly in one shift. So your whole design criteria change. You want it to run for a long time. So that is a major challenge. You want to maximize capacity, high flux, less critical, and you need to establish protocols, what pressure, what flux, so forth. Okay? So that brings me to the end of sterile filtration. So we could, I guess, ponder a question I had. And after that, we can, we're supposed to stop at 1:15, right? So we, is it 1 o'clock? Or?
Yeah, we can stop at 1.
Okay, all right. So I had a few questions here. Some of these actually, I think we need to have a few more lectures before we do it. But here's one question that I think maybe you can try and answer for me. So briefly describe the differences between normal flow and tangential flow filtration. So I've said here, give examples of each of these modes of operation. Are both modes of operation used? So we've just finished talking about this, so maybe I can write that here, right? Okay, so what I'm saying is this. So can I write on this, or this is black now? How do I make this? I go to which one? Here? Oh. Yeah. Okay, good. Oh, thank you. So we have normal flow and look very good. Tangential flow. So let's start to make a list here. So if we look at normal flow for microfiltration, can they be both used for microfiltration? Yes. Okay. So microfiltration. Let me do it like this. Microfiltration. Wow, it doesn't come out very well, right? So they're both used. Okay. What particular application for normal flow? Anybody? So we've said that we can use normal flow for microfiltration in the biotech industry. What application? What unit operation? Depth filters, okay. What else? Sorry? Sterile, yep. Okay, what about tangential flow? Really, it's competition with depth filters, right? So it's going to be, let's just say, bioreactor harvesting. Okay, now things we haven't talked about yet, but I'm going to add them so that we have a what's coming. So ultrafiltration is actually here, okay? So ultrafiltration is run in tangential flow. Normal flow ultrafiltration, do we do it in the biotech industry? We do, but it's only to screen membranes, okay? So you get membranes from different companies, and if you were a process engineer, you would want to check them quickly. So you don't want to waste a lot of your protein, okay? So you do quick scaling studies with these, okay? Quick checking time, but basically not in operation. Virus filtration, we will learn soon, is always normal flow. Okay, so virus filtration is always normal flow. So you can see both are used, okay? So next question is, let me clear this. Is that, yes, and does it still work? No. So back to this and back, right? Oh, is that okay? Yes, so that's fine for the moment. Okay, so let's look at this. So these are normal flow, and this is tangential. And this is too thick. Yeah? What do I have to change? Okay. So normal and tangential. So normal flow, let's just put these as advantages, say, right? So what are some of the advantages of normal flow? Anybody? Less, that's a good point, yeah. Probably less. Yes, less aggregates. Less aggregates, but the disadvantage to that, it's the not continuous though, right? Right, it's not really a continuous. You can't do continuous biomanagement so easily. But you're right, you don't get aggregates because here you can get aggregates due to pumping and so forth. So the difference here is just removing stuff and then what goes through goes through. Okay, others, either way, advantage or either side. Who can give me some? Sorry?
It's a quick method to access mapping problem.
Yes, yes. So this is good for screening. Screening studies, yep. So let me add some here. So one thing that's good about this one is it can be made continuous. Okay, another one is that you can reuse the membrane, which may be an advantage, it may also be a disadvantage, right? It's an advantage because obviously that's good. You can save the membrane, microfiltration, ultrafiltration membranes used many, many times, okay? The disadvantage, of course, is that it's not one-time use, and there is movement today towards single-use operation. I'll talk about single-use ultrafiltration actually maybe on Thursday. So that's another reason, yes. Other things.
Low fouling tendencies.
For this, yes, low fouling tendencies. And actually, I'm just going to put here biooptimal, which is an attempt to try and combine the two and get the advantages of both. Okay? Anything else? Have we done everything, do you think?
Protein denaturation is possible.
With tangential flow, yes, yes. So we can get protein denaturation, yes. And one of the things that here is you use sterile filtration here, and so there it's basically like a guard filter, right? Good. So I think those are the differences between these two, right? So I think that's an important point that we get from this work. I had another question, but I think I'm going to hang on to it until we finish the next lecture. So I'm going to start now on some of the other stuff. Let's do a little bit of that because it's till 1, right? So we can start a little bit on that, and then when we get to the next tutorial session, we can do the next question. So let me therefore close this, right? And I need to reproject, I guess, right? What happened here? Okay, good. So the next lecture then is sterile filtration. So 5 is this one. Good. Okay. So we've talked about dead end or normal flow filtration. There's tangential flow or cross flow, and these are both used for microfiltration and ultrafiltration, as I just tried to point out. Okay. So this is a reminder. We've seen this many times. So I'm going to skip that. So tangential flow microfiltration, also called cross-flow microfiltration, competes with centrifugation and depth filtration, expanded bed chromatography. Oh, what happened? I thought I had. Hang on. Sorry. Oh, I see what's happened. Sorry. Okay. Is it there now? Yes. Okay, good. So as we've said before, this tangential flow competes with these other processes, centrifugation and depth filtration. Now, tangential flow microfiltration, now let's think of this just for bioreactor harvesting. I talked to you about the biooptimal filter, and that, if you remember, had like a 40 micron pore size going to about a 0.4 micron. Yeah. That is relatively large. Usually it's about 0.2, and that should be a mu, 0.2 micron, okay, not millimeters. So that is an optimum size. If you use something bigger than that, the problem is there's a risk that cell debris or the small particles may get through. And I told you one of the advantages of microfiltration is that that doesn't happen. you don't need to use anything else. You just use this, you take what comes there, and you run it straight into the next chromatography column. So, I mentioned that today tangential flow microfiltration for a while was not very popular because of higher cell titers led to greater fouling, which meant then this is plugging all the time and not working. So one way people tried to get around that is use larger pore sizes, which is great. You can do that, but then there's a risk you do something else after that, and then the advantage is lost. So typically, we try to use 0.2 micron pore size membranes to generate a filtrate solution that requires no further clarification. Okay? Oops. Okay. I guess we can keep going, right? So competing technologies are used in conjunction with normal flow, usually depth and sterile filters, to achieve high levels of cell debris removal to protect subsequent chromatographic columns. So competing technologies are things like centrifugation. Okay? High density cell cultures, which have much higher levels of cell debris, have created major challenges in the application of microfiltration as the initial clarification step. So the behavior of tangential flow microfiltration is dominated by something called concentration polarization, which one of you already told me you knew about that, which is good. It's basically the reversible buildup of rejected species near the membrane surface, and I'll show you more of that in a second. These phenomena are avoided by operating at low filtrate flux below the critical flux for fouling and or exploiting inertial lift effects. So let's put a diagram here and try and explain this. So I think some of you know what this is about, but let me change the color. Good. So does it draw here? Yes, good. So here's your microfiltration membrane. The feed is coming this way. You're drawing permeate through here. This is permeate, that's the feed, right? And so concentration polarization means that you have particulate matter all around here, but there is a net drag force pulling it to the surface. Why? Because you have permeate flow there, okay? And so that leads to, if you like, what we call something like this, where this is the concentration polarization layer. In other words, there is a boundary layer that forms. So for those of you who are not engineers, this is very much into transport, what we would call transport phenomena, okay? So there's a boundary layer that forms. What we're trying to say by this boundary layer is that basically, qualitatively, there's going to be a higher concentration of particles near the surface because they're being drawn to the surface. But we like to quantify that. The reality is that this slowly becomes less, and in the center of the tube, it's the minimum, and this is the tube, so you'll also have this boundary layer on the top surface as well because you're pulling stuff from both sides, right? And so it's a continuum. However, in engineering terms, we find that difficult to work with. So we'd like to say there's a resistance due to this deposition, or not really deposition, reversible association of particles near the surface, right? They're not deposited. Depositing is a cake. It's a reversible association. But we say that basically if you draw a curve like this, say 90%, 95%, some number like this of the resistance is now within this, okay? So it gives us a way to try and quantify it. So that you get this concentration polarization layer that forms, okay? And what happens then is that this actually is going to somehow limit the flux. Now in tangential flow microfiltration, or in any of these, we said that the growth of this concentration polarization layer is going to be limited, right? It's limited by the fact that you have fluid flowing this way. So if you think of it, this is my original membrane. I'm pumping this way. I'm starting to get a cake layer formed on the surface. I'm starting to get a concentration polarization layer forming, right? But as that happens, I narrow this tube, right? The diameter of the tube narrows. Now, if I'm still pumping at the same rate, as the tube narrows, the velocity here must go up, right? Because if you do consummation of mass, you want the same amount of stuff to go through, but you've got a smaller tube now. So it's got to go faster. If it goes faster, it's going to have a bigger effect on trying to take stuff from here and drag it along with it, okay? So this is this sweeping effect. In other words, in mathematical terms, we say the wall shear rate goes up, okay? That's what we call it. So if the wall shear rate goes up, you're shearing more stuff away. So it's like a self-controlling mechanism, right? The more that deposits here, the faster this starts to go through, the more the wall shear rate goes, the more it starts to suppress cake formation. So that is the whole beauty, if you like, or the idea of tangential flow microfiltration. You limit cake growth because you have this shearing on the surface. Okay, that's why this is appealing compared to dead end filtration. All right, now something else to think about. So initially, when people were studying tangential flow microfiltration, so this goes back into some of the papers you can look at, say, in the like late 70s, early 80s. Because remember I told you the first biotech product was about 82. So it's around that time people were trying to work on these sort of things. They said, well, let's do it this way. Let's say that you have convection towards the membrane and you have back migration, because obviously if something is coming, it's got to be moving away, otherwise it's going to grow forever. Now, if we think of diffusion processes, we say diffusion is driven by a concentration gradient, right? So we would say, okay, the concentration is higher here, it's lower there, so we can define a back diffusion coefficient, a diffusion coefficient away from the surface. And what's the most common diffusion coefficient we talk about? It's a Brownian diffusion coefficient. So does everyone know about Brownian diffusion coefficients, right? They are basically determined by things like Stokes-Einstein equations and so forth. But they are due to random thermal motion, right? So random thermal motion, you have a higher concentration here, lower concentration here. So things are moving randomly, but they tend to move down the concentration gradient. So people did this for microfiltration, and they had a problem because you end up with something called the flux paradox. That's what it's called in the literature. And that was this. You can do these predictions and say, okay, you can look at the convection this way, and you can look at Brownian diffusion this way, and you can predict your permeate flux. That can be done. Unfortunately, the permeate flux you predict is smaller than what you observe in reality. So that's one of the rare cases where actually in reality you get a much better result than you predict. So this is a problem. And so the reason is this. This is for microfiltration. So for microfiltration, you're talking about particles, right? So let me draw this again now. So here's this. You're talking about particulate matter, micron-sized particles, say, that are moving there, okay? Now, the Brownian diffusion coefficient, if you may remember, goes inversely with the radius of the species. But for micron-sized particles, if you try to calculate, and you can do that, you'll find it's tiny, okay? Brownian diffusion works very well for proteins, for small species, for sodium chloride, things like this. For micron-sized particles, it's tiny, okay? So the problem is then the Brownian diffusion coefficient is not very well predicting the back migration. So what is causing back migration, okay? We talked about the shear stress that's trying to drag stuff through. So we could perhaps hypothesize that this cake is moving, okay? And the cake is moving along this, so there's some sort of movement. Maybe that's happening, but that still doesn't really explain too clearly how stuff is coming down here, right? There is a cake movement, that's true. So there are some other mechanisms that are important here, and so these I'll try and explain qualitatively. So one is this. I don't know how much you know, but if you have a flow field like this, and you have laminar flow like this. So laminar flow means you have a parabolic flow profile. What that means is that as fluid is flowing this way, the fastest velocity is here and the lowest velocity is in the walls, because the walls are not moving, so the fluid wants to try and get stuck there. If I have a particle that's in here, okay, it will feel a different shear stress on the two sides, right? Because fluid is moving slower on one side, faster on the other side. And this leads actually something called inertial lift effects. It means the particle will tend to move, okay? And it will move to a streamline where it is going to be, these two forces are matching, and also what has to come into account here is the buoyancy of the particle and various other things. But just imagine that if you had a parabolic velocity profile where nothing is moving at the walls, it's moving fast in the center, and you were in the middle of that, right? You will tend to move to a position whereby somehow the shear stresses are balanced, okay? So the hypothesis here was that if you have particles moving here, the same thing happens, and there is this net back migration effect. So there's inertial lift forces. That's one thing. There's another thing that can happen, and that is if you have a particle here, we talked about the shear stress acting. So there's a shear stress acting to pull it along, and here there's a lower shear stress that will also tend to cause it to expand and move away. So that's called shear-induced diffusion. So basically, there are these various mechanisms, and these are not just made up. These are real ones that you can actually go and you can study, okay? And then they are shown in fluid mechanics. So the point is, for microfiltration, when there's particulate matter, there are many back migration mechanisms, okay? So there's shear enhanced diffusion, there's inertial lift effects, there's Brownian diffusion, which is minor, and then there is also this cake flowing along the surface, okay? So all of these actually come into the theory of microfiltration, and all of them can be used to, because what you want to do is predict the flux. So they can predict the back migration, okay? And so I said here, concentration process fouling effects, filtrate flux limited by accumulation of concentrated layer of cells and cell debris at the membrane surface. These phenomena are avoided by operating at low filtrate flux, below the critical flux, and or exploiting inertial lift effects, maintain particle-free zone near the membrane surface. There's another thing that people talk about, which I should mention, and that is, if you think of this, what people say is, okay, the reason you're getting this cake layer forming is because you've got a net flux in this direction, and this flux causes convection towards the surface. There are also these back migration mechanisms. So people hypothesize there's a critical flux. If your flux is below the critical flux, you will not get deposition because these back migrations are very effective. If you are above the critical flux, you will get deposition, okay? But again, the deposition won't occur forever. It'll stop at some point because this channel is becoming more narrow. But you will get deposition, okay? So there's a lot of literature on this critical flux idea. I would say this, it is an interesting concept. It gives you some idea in real applications, at least qualitatively, what would be a good operating condition. But in reality, it's very hard to use, because just like the blocking models, critical flux assumes the particles are non-interacting. Unfortunately, all these biological particles are rather sticky. So one will stick on the other, will stick on the next, and so they're not non-interacting. That is not true, okay? Secondly, you've got a range of particle sizes. That's also a problem, okay? Because the critical flux idea, again, all of these back migration mechanisms also depend on particle size. And so different particles will have different forces acting on them. So critical flux is a nice idea, but actually coming up with an actual critical flux for real systems is very difficult. It's easier to do it with say, latex particles or something like this, okay? So we can talk about critical flux. So at steady state, the rate of cell transport to the membrane is balanced by the rate of back migration. Brownian diffusion is typically negligible. Let me get my pointer going again. Okay, Brownian diffusion is negligible for large cell and cell debris, and thus back transport is determined by the effects of shear-induced diffusion and or inertial lift. And so I've talked now about shear-induced diffusion. So shear-induced diffusion refers to the random diffusive motion arising from particle-particle interactions in a shear flow of concentrated suspension. Shear flow causes particles on neighboring streamlines to interact or collide, leading to transient displacement perpendicular to the flow. So that's fairly complex, but basically the theory of fluid mechanics would predict all this, okay? So these are just other back migration mechanisms. Now, this particular equation here is for shear-induced diffusion. Oh, what happened? It stopped moving, right? Session video audio connected, reconnecting, connected. What happened? No, it's still not moving. Should I just stop sharing and share again? It's working? No, it's... No, it stopped. Let me stop sharing and try again. Oh, I stopped sharing, but it still got that there. Okay. Let's see here. Where is my lecture here? Okay, now it's back. Good. Okay, thank you. So okay, so this I didn't want to get into too many equations again, but this one is sort of important because this is the one for shear-induced diffusion. And so what I wanted to point out is that all of these equations have slightly different forms. So in the case of shear-induced diffusion, you have a flux. So you have the flux, right, which is equal to, this is the particle radius, and this is the length of your channel. You can see the flux varies with like particle radius to the 4/3 power. In other words, the flux increases for larger particles. But Brownian diffusion, the back migration would decrease with larger particles, okay? So shear-induced diffusion, quite a different mechanism. The larger the particle size, the greater the back migration. That's why I was saying Brownian diffusion for micron-sized particles is irrelevant, okay? And then you can see it also depends here on gamma W. Gamma W is actually the wall shear rate, okay? So if you're pumping faster, you'll get greater back migration. So greater back migration, smaller K clear, and it means higher fluxes, okay? I've said here, inertial lift arises from hydrodynamic interactions associated with distortion of fluid streamlines and the gap between the particle and the flow boundary. I gave you a simple explanation of that earlier. The inertial lift velocity is proportional to the cube of the particle radius and so forth. But let's look at this figure. This is what the nice, oh, it's stuck again. So why did it get stuck again? If I cancel this, it should work, right? Yes, okay, good. So this is a nice figure because what this probably does is summarize everything for you fairly qualitatively. So this is flux. Oh, I've got to do this again. Okay, so this is the flux and this is the particle diameter, all right? So this is assuming that these various back migration mechanisms represent the removal of particles from the surface, and therefore we can predict the flux. So if you go with Brownian diffusion, you can see this is the predicted flux. It decreases with increasing particle diameter. Please note this is a log scale, okay? So this is 0.1 micron, 1 micron, 10 micron, okay? So Brownian diffusion is becoming very, very insignificant for micron-sized particles, okay? You can see here the flux is decreasing rapidly. If you look at shear-induced diffusion, and by the way, this is the Brownian diffusion, how it varies, okay? So there's a viscosity, a length. You can see that it varies inversely with particle radius. A is the particle radius and so forth. And if you wanted to, you could calculate that from Stokes-Einstein equation and so forth, okay? If you look at this one, this is going to be shear-induced diffusion. And you can see here that it's roughly equal to, it goes linearly with wall shear rate. Okay, this one goes with wall shear rate to the 1/3 power. It increases with particle radius. This is decreasing with increasing particle radius. And both of them depend on the length to the inverse 1/3 power. So here's another interesting point there. It means that actually if you want to maximize your flux, you want short fibers or short membrane paths, not very long ones, right? Because you can think of that, the longer the path, the greater the concentration position boundary layer forms. The other side of it is that if you have it too short, it's going to be a huge expense, right? Because you've got modules in series, you've got to have connections, so there is a trade-off, okay? But long modules, basically, you pay a price with lower average fluxes. If you look at inertial lift, you can see inertial lift actually doesn't depend on the length of the module at all, but it depends very strongly on wall shear rate and particle radius, so it increases rapidly. So what this means is if your particle radius is about 10 micron, you're probably getting equal contribution from shear-induced diffusion, inertial lift forces. Larger particles, inertial lift dominates, okay? Now, this is nice, and I think this is very good when we are learning the theory. As a practicing engineer, you'll probably never use that because there's a problem. Again, this is like the blocking model. It's an idealized solution system, right? We're talking about uniform particles, non-interacting particles, right? Cell cultures, there are a range of particle sizes. So now you're going to have to somehow find an average for a huge number of different particles. But there's a bigger problem. They're interacting. They tend to stick to each other, okay? So typically, you will just use some sort of fudge factor for the back migration. But it's important to understand this theory because it does give you some ideas, okay? Large particles, you know that Brownian diffusion won't be important. So for large particles, it may then you could have as long a fiber as or channel as you want. It won't have such a big effect. I mean, it gives you some ideas like that, okay? So comparison of predicted filtrate flux based on Brownian diffusion, shear diffusion, inertial lift forces. These calculations were done at a nominal wall shear of 5,000 reciprocal seconds and a length of 20 centimeters for the module. Now, we mentioned this idea of critical flux. Critical flux is based on analysis of data for tangential flow. Oh, sorry, I forgot again. Right, okay. So critical flux, and I mentioned this earlier, it's a concept that comes up quite a lot. And it's based on analysis of data for tangential flow, microfiltration of yeast cells. Okay, that's how it was really brought up in the biotech area. But yeast cells are really a very model system. Okay, so I always think of it like this: the best model, if you like, is latex particles because they're non-interacting and they're uniform size. And the next best model, if you want a biological system, is probably yeast cells. They're relatively uniform, except they start to bud, but they're relatively uniform. They've got a cell wall, so they're relatively incompressible. They are fairly robust. They don't lyse that easily, so they're probably the second best model. But they do interact, okay? They do interact. And so based on that, you come up with this critical flux hypothesis that there exists a flux below which fouling is negligible, and there will be no measurable decline in flux or increase in transmembrane pressure with time, okay? So if you run at below this flux, presumably you could run for hours and hours and hours and not see any big change. If you run above that flux, there will be some deposition and there will be a decrease, and it should reach steady state again at some point. Now, the value of the critical flux depends on the device hydrodynamics as well as any long-range electrostatic interactions between particles and the membrane, and that's where the trick comes in, because if it's not non-interacting, then this starts to change things a lot. Several recent studies have shown that a low level of fouling can take place even below the critical flux. But that actually makes sense, right? Because for real particles, there will be interaction. So even below the critical flux, you'll get a small amount of fouling. Another way of putting it is you can never run this thing forever, right? You are always going to get some fouling and eventually it'll stop. So fouling under these conditions may be heterogeneous. Distribution in local flux over the surface of the membrane with high flow rates in certain areas and others in the others. Okay, what that means is this. So another problem is the membrane surface itself is not homogeneous, right? So there may be certain, and this actually is noticed a lot in reverse osmosis and why scaling occurs in certain places. So some places you might have higher fluxes on a local basis than other places, right? Where you have higher fluxes, you might get more fouling than other locations. And so this leads to basically fouling and this low level of fouling we're talking about. So you don't have a perfectly uniform membrane, you don't have perfectly uniform particles, and you don't have particles that are non-interacting, okay? All right, so let's talk then a little bit about the various sorts of membranes. So we have narrow bore hollow fiber membranes for tangential flow microfiltration made from polymers including polysulfone, polyether sulfone, polypropylene, PVDF, and mixed esters. I think all of you have seen hollow fibers. So basically, these are the fibers here. If you look at these are going to be little tubes like this. That's what these white things represent, and they've got porous walls. Your feed flows inside here, and you remove permeate from the walls. Okay. They are potted so that at this end, this is epoxy or a polyurethane, which prevents anything outside the fibers from going through this port. Because this port is the port that connects with the lumen or the inside of the fibers. You remove permeate from here, and typically there'll be a permeate port somewhere here where you take stuff out from the outside. So this is providing a barrier, okay? Oh, I need to turn this off, sorry. Okay. Fibers have inner diameters of 0.2 to 1.8 micron, that should be micron, sorry, μm, providing laminar flow with moderate shear rates. Most hollow fibers, let me get my pointer back. Most hollow fibers have asymmetric structures with dense skin at the lumen side of the fiber, inside out. What do I mean by that? So you have a fiber like this. The filtration layer is on the inside, okay? There is an example of a reverse. I talked about biooptimal. There the dense layer was on the outside, but typically it's on the inside. Okay, that's called inside out. The flow is from inside to the out. There are, by the way, a couple of applications where you have outside in, where you have flow from the outside going inside. That actually exists for nanofiltration membranes. And then the dense layer is reversed. Okay, it's a bit like using the biooptimal. Fibers are self-supporting, so they can be cleaned by backflushing from the filtrate side. Okay. Pre-sterilized disposable hollow fiber modules have been developed, eliminating the need for cleaning and regeneration. And we'll talk about that later, but these are one-time use modules that have been developed. But generally, these are reused. Use it once, you stop, clean in place, validate that they have been cleaned, reuse. Okay. Flat sheet membranes can be cast on non-woven substrate and have either isotropic or asymmetric structure. The range of polymers is very similar to what's used for hollow fibers. So there's polysulfone, polyether sulfone, cellulose, hydrophilized PVDF, and so forth. So they're very similar. Materials often surface modified to increase hydrophilicity and reduce fouling, and they can be cast as mixed polymers with the various additives put in here. Membranes can directly be bonded or glued to plates or sealed using appropriate gaskets. Open channel systems commonly employed for tangential flow microfiltration to minimize plugging by cell aggregates and debris. So actually in the biotech industry, we don't use spiral wound modules. Okay, so spiral wound is not used. It's mainly going to be either tubular membranes, so tubular means large tubes, hollow fibers, which are small diameter tubes, or flat sheets. And each has their advantage and disadvantage. Okay. So the reason spiral wound is not used is that that is fine for, say, reverse osmosis, where you have no particulate matter present. But the minute you have particulate matter present, they are very hard to clean, they easily foul. The advantage of them is they are very high density. But if you look at these others, we could actually do a table of this. So hollow fibers are nice because they're actually fairly compact. You can get a lot of membrane surface area into a small footprint. Not as high as spiral wound, but still pretty high. Downside is if you have particulate matter that can plug the lumen of the fibers, that can go in, they're big enough to block these lumen, and we said the fibers are what, 1.8 millimeters or so forth in diameter. If they block those, it's very hard to clean. On the other hand, flat sheet membranes that are put in stacks like this are much easier to clean, but they have a larger footprint. Okay? And tubular membranes are somewhere in the middle. So they are larger tubes, they're easier to clean, and they have higher surface area. They're not as common, but they are also used. Okay. Non-steam in place. So tangential flow microfiltration modules used in both sterile and non-sterile processes. Several sterilization methods include chemical, superheated water, autoclave, and so-called steam in place, where you clean them in the setup. You've got stainless steel housings and things you steam in place. So steam in place is the most common one. It's the most convenient method of sterilization for large-scale industrial microfiltration systems. Steam in place microfiltration modules specifically developed for sterile cell protein separations. Remember, I told you that these are if you're not using one-time use devices, you clean them, you have to sterilize, you have to validate that they are clean, then you can use again. And you don't want any cross-contamination, right? So this is actually very important, that they can be steamed in place. So this is a typical example of what they look like. This particular one is shown here for steam in place applications. And so one can take lots of these and I should go, sorry, I meant to say this. One can go here and one can stack lots of these in series, you see, and that way you can increase your membrane surface area. Okay. So medium exchange and perfusion. So tangential flow for microfiltration systems used to carry out cell protein separation process, including medium exchange during fermentation. The process originally developed for production of recombinant human tissue plasminogen, or TPA, by Genentech. So that was a long time ago when they were first used. And if you look at Harvest, the same microfiltration technology that was originally developed for medium exchange has also been used to harvest recombinant DNA-derived proteins from mammalian cell cultures. So we've talked quite a lot about that already, right? The applications of this. These two figures show you a large-scale microfiltration system for harvesting or recovering DNA-derived proteins from Chinese hamster ovary cells The first one on the top A is a microdyne 0.2 micron, again, sorry, the mu is missing, polypropylene hollow fiber microfiltration system with 174 meters squared membrane surface area. Actually, if you think about that, that's a lot of membrane surface area. Okay, that's pretty big, and so imagine trying to run all that in a sterilized form, in a sterile form, having clean in place. So when you clean it, you have steam coming in, you clean, you've got to remove all these solutions. It's quite a lot of equipment and quite a lot of connections. The lower one is a millipore ProStack flat sheet membrane system with 186 meters squared of 0.65 micron size hydrophilic PVDF membrane. So this is a fairly large pore size, 0.65 micron. Okay. Single-use systems. How are we doing for time? Maybe I'll finish this and then we'll stop. We're almost there. So single-use or disposable systems for bioprocessing are supplied in ready-to-use format, pre-sterilized either using gamma irradiation or ethylene oxide gas. So you can see the advantages of pre-sterilized units, right? They're pre-sterilized. So that means when you get them, they are sterile. Until you open it, they're totally sterile. And the idea is it's in a sterile package. You take it, you attach it to your system, and then you just use it. Okay? And then when you finish, you take it out and you throw it away. So you can see that saves all that stainless steel equipment I showed you in the previous slide, right? Sorry. Where was it? Here. All this stainless steel equipment and all of this tubing and all that you can get rid of now, right? So there's a great advantage in using this one-time use sterile equipment. Eliminates the need for subsequent steam sterilization and cleaning, significantly reduces energy costs, water usage, disposable environmentally challenging chemicals. So there are tremendous savings in that sense. Capital cost of single-use systems significantly lower than for stainless steel installations. Facilities can be brought online more rapidly to reduce manufacturing timelines. And that actually is quite important in any industry. You don't want your equipment just sitting around, right? The more you're using it, the better, right? If it's sitting there, it's just depreciating and there's nothing happening. Adoption of single-use technology generally facilitates changeover in multi-product facilities, minimizing turnaround time while significantly reducing the risk of cross-contamination. And I told you that in the past, companies, when I say past, maybe 20 years ago, you'd build a manufacturing process for a drug, and you'd run it, and you'd make enough drug in maybe, I don't know, 6 months or something, it depends, and that's enough for the next 3 years. So then what do you do with this facility after? It's just sitting there, right? You'd like to use it for something else, and typically large biotech companies have many products. But to switch over and use it for something else is a major exercise, because now you have to make sure there's no cross-contamination, you've got to clean out your columns, take out all the resin. You can't use resin that was used for one drug for another drug, okay? That's a huge amount of work. So if you use disposable systems, that's very simple, right? You just put a new system in there and run. And so, so there are significant advantages here. And this risk of cross-contamination is very, very important. You've got to avoid that. So it greatly enhances the manufacturing flexibility, improving the ability to respond to fluctuations in demand, which is also something that's important these days. So this is an interesting point. Single-use systems make up about 85% of equipment employed in production of preclinical materials. So I'm not sure how much you know about regulatory affairs here, but when you're making a new drug, okay, so if you think of the timelines often, so, you know, recently we came up with these vaccines for COVID-19, and that's quite amazing that they came up in like a year and a bit. That's really unbelievable, because usually these things take years and years, okay. Well, another reason is that they weren't really approved by the normal processes. They were sped up. But anyway, if you're making a drug, so typically what happens, you start off with what they call research, which research really means cell biology and things like this, where you're looking at the therapeutic effects of this drug, and you figure out that it may be something useful. Okay, fine. So after that, you have to make it, because if you're going to do any of this testing, you have to make the product, right? So you make it for what's called preclinical testing. So preclinical is when you test it on basically different sorts of cells, typically not actually animals. You just look for therapeutic effects, you look for side effects, but it's before any clinical testing. And once you pass all that, you then submit various documents in the US to FDA or whatever regulatory authority to start your clinical testing. And then you have phase 1, 2, and 3. Okay, and so phase 1 will be some sort of, say, actually not even animals. Phase 2 is probably animals, and you got phase 3, and then you got human clinicals and so forth. But every time, the amount of product you make increases. Now, if you think of it, this is kind of complicated because in the meantime, you're developing manufacturing processes for this drug. And remember, the regulatory authorities are going to want you to make sure that whatever manufacturing process that you end up with has also been validated. So you don't want to change processes too much once you start clinical testing. And so you're starting off with making small amounts and it gets bigger and bigger. So what this means is that 85% of production of preclinical materials is used as these single-use systems because it's easy to throw it away and it's easy. But there is increasing use of using them for large-scale manufacturing and also to support clinical trials. So growth in the market for single-use systems in bioprocessing is 5.44 billion in 2021 and projected to grow by 20%. Almost all, well, we talked about this, normal flow filters originally designed as single-use systems include sterilizing grade and virus removal filters. They're all single-use, okay? I'm trying to think. Okay, let's go a little bit further then. Ultrafiltration used for protein concentration and buffer exchange. So ultrafiltration also uses tangential flow filtration. High protein retention achieved by using a small pore size membrane, although recent studies have demonstrated the potential of exploiting both size and electrostatic interaction for enhanced ultrafiltration processes. So ultrafiltration is a size exclusion process. We have a membrane pore size. We reject based on the pore size, right? But if we modify the surface, we can actually get inverse results. So we can get larger species going through, smaller species being rejected, basically by putting charge interactions on this, okay? So obviously the pore size will let the larger species go through, but nevertheless we can get selective rejection of a smaller species. And so there's quite a lot one can play with surface properties. Membrane permeability is evaluated from the water or buffer flux as given by the following expression, where the permeability is just the flux divided by the pressure, okay? Analysis of data in tangential flow filtration device is more complicated than conversion of feed flow into filtrate and creates nonlinear pressure drops within inside the module. Let me explain what that means then. So let's see. Okay, so membrane permeability is derived from water or buffer flux as follows. So the flux we are saying is equal to the pressure driving force divided by a resistance, and all this is saying is the permeability is then the flux divided by the pressure driving force, okay? Analysis of data in tangential flow filtration devices is more complicated since the conversion of the feed flow into filtrate flow creates a nonlinear pressure drop on the retentate side. What do we mean by that? So here is our, if we're using say a hollow fiber or a channel, right? And so you have feed coming this way and you have permeate flowing this way. And so by conservation of mass, the amount of volume here is actually decreasing, right? Because you are removing some of the liquid. So, but you can't create mass. You can't have an empty space. So the relative velocities here are going to be changing, okay? Because you've got to have conservation of mass, okay? So this will create a nonlinear pressure profile. So actually we talk about a feed pressure. So feed pressure, we talk about retentate pressure. So this is going to be retentate pressure, and we talk about a permeate pressure. We take the average of these two and subtract the permeate pressure, and we say that's a transient pressure drop. That's okay, but the reality is you have something that's doing this, right? You know, the feed pressure, it decreases, I've exaggerated, but you get to the retentate side. So the transmembrane, instantaneous transmembrane pressure drop is changing along this module, okay? And that becomes quite important because then you can have different amounts of concentration polarization. If you have a range of particles, you get a different amount of fouling. And so something I'll talk about on Thursday is something called high performance tangential flow filtration, where we try to avoid this change in TMP along the flow channel, okay? The measured permeability scales as a reciprocal of solution viscosity and effect that can be significant with concentrated solution. I've mentioned that already, right? As the viscosity goes up, the permeability will change or the flux will change. How much more should we do? Shall we stop at this point? Let me stop at this point. and then we'll I'm just trying to see how much more I had here. Yeah, we can pick it up from, okay. What we will do is when we come back, we will start another problem that I have. And this is a fairly complex problem, so you can think about that. And then we could either do some more of this or however we like to do it. Because I think we covered quite a lot today. So we'll stop at that then, okay, and we'll have lunch. Okay, so anyone online has any questions? Or I'm afraid we've ignored all the online people. All right, thank you. And I will escape this.